Good morning, grade 12s. Today we're looking at work, energy and power, and we are going to discuss your questions, but I really want to tell you I have not received enough questions yet. Please remember to send us your questions at juniortukkie@up.ac.za. We really want to answer your questions in these sessions. Now, most of the questions that I did receive were centered around conservative and non-conservative forces. And that's what we're going to look at today. Now, let's start off by looking at the definition of a conservative force. A conservative force is a force for which the work done is independent of the path, right? Now that first one is the one that you will find in the exam guideline, and we did that one on our study material as well. I always prefer to use the one in the guidelines, but there's another one, and for instance last year they accepted this one as well, and that is that a conservative force is a force for which the work done in moving the object, and now it is in a closed path, is 0. So the first one is all about moving between 2 points. So let's call them A and B, right? So the first one said that the work done by an conservative force is independent of the path. So it does not matter if you do that or you do that. The work done by a conservative force will be the same for both, right? So it doesn't matter how you move between A and B, it's independent of the path taken. That's the first definition. The second one tells you that the work done in moving in a closed path, so I'm moving from a specific spot and coming back to that same spot, and then the work done by a conservative force will be 0, right? So we want to do this example to show the first definition. So we've got a spot A and B, and I'm going to start out by working out straight from A to B. If I'm moving this object straight from B, what will be the work done by my conservative force? Now, conservative force, you've got 3 examples, right? You have gravitational force, you have electrostatic and elastic, right? And the only one here that's involved is gravitational. So I want to work out the work done by gravity to move this 10 kilogram object 2 meters from A to B. So if I'm moving that, remember, the work done will be the force times the displacement times cos of the angle. Right, gravity here will be 10 times 9,8. The displacement will be 2 meters, right? I'm moving 2 meters. And then cos, now remember that angle must be between the force you are working with, which is now gravity, and the movement. So I'm working with gravity, and gravity is straight downwards, and I have to work with the angle between that gravity that is straight down and the movement up. So I need that whole angle, right? So that is now 90 plus that bottom angle. So this is going to be 90 plus 30. Right, and if you work that out, you end up with minus 98 joules. Did I expect the minus? Yes, because gravity is not helping this movement, right? It is removing energy. So the negative does not indicate direction, it indicates that energy is removed. Right, so this is when I'd go from A to B in a straight line. So let's call that route A, going in a straight line from A to B. So now, next up, what I want to do is I don't want to go that route. I'm going to try a new route. So let's try going horizontally and then going vertically, right? Going horizontally and then going vertically. So now the work done by gravity for route B, right, let's call this B, is going to be the work done on this horizontal part, work done by gravity on the horizontal part, plus the work done by gravity on the vertical part of the movement. Right. Now, let's talk about the horizontal part. Now, for a horizontal part, you will have gravity times delta x times cos theta. Right. Gravity over here, you can work that out. let's just talk about that angle. Now, what is the direction of gravity? The direction of gravity is straight down. And what is the direction of movement? To the right. So what is the angle over there? 90, right? And remember, the moment that you've got a 90-degree angle, then no work is done. So gravity is not doing work on the object when it is moving horizontally, because it's perpendicular to that movement. So that is a 0, right? And then we are looking at the vertical part. Now, I don't have that distance, so let's just quickly say, if I've got that angle, 30, I can work out that height, right? If I say sine of 30, that will be that height divided by 2, right? Opposite over hypotenuse. Right, and then if I work out that height, it ends up being 1 meters, right? So here I will say it is 10 times 9,8 for the force, times 1, right? Times, and now cos, and careful, gravity is working down, and I am moving up, right? So the angle I need over there is cos 180, right? Cos 180, which is just the minus. So I end up with minus 8 joule. And the total energy needed for this journey is also minus 98 joules. So it doesn't matter if I move in a straight line, route A, or I move route B, the energy required, the work done by gravity will be exactly the same. Right, so that was definition 1. The work done by a conservative force is independent of the path. Right, between 2 points, it doesn't matter what the path is. Now we want to look at the second one. Now for the second one, let's start off with that same inclined plane 30. We've done that already, moving that 10 kilogram thing from A to B 2 meters away, right? I've already done that. So let's just recap. What was the work done by gravity from A to B? That was Fg delta x cos theta, and that was 10 times 9,8 times 2 times cos, and that was 90 plus 30, and we ended up there having minus 98 joule. Remember that one? Okay, we've done that just now. So, okay, so now I want to go, and for the second one, they're talking about a closed path. So I've moved from A to B. If I now move back from B to A, I'm ending up at the same spot that I started with. So that will be a closed path. So now I'm going from B to A, and I want to work out what is the work done by my conservative gravitational force. That will be Fg delta x cos theta. Right, so that will be 10 times 9,8 times 2 times cos, and now very careful, we are now moving down, right? So what is the angle between gravity, that is straight down, the force we're working with, and the direction of movement? So we're working with that angle, right? And that was 90 minus 30. Right, so you're actually working there with an angle of 60. And when you do that, you end up with 98 joule. And now it's a positive. Does that make sense? Yes, because gravity is helping this movement. It is going to give it movement energy, right? So let's talk about the whole movement. If I move from A to B and back to A, the work done will be minus 98 and then plus 98. So altogether the work done will be 0 joule. So if I have a closed path, then the total work done by my conservative force is 0 joule. So there you go, guys. That was the 2 definitions, and to be sure, they are really true. Right, so what are we going to use this for? Now, first off, let's talk about if I have an object of mass m and I'm throwing that up into the air, moving it up into the air at height h, then I want you to work out two things. The first thing I want you to work out, what is the work done by gravity during that movement? And I also want you to work out what is the change in potential energy. Right, now work done will be Fg delta x cos theta, and the gravity is just m, the mass, times g, right? The displacement in this instance is only the height. And now I get to cos. Now be very careful. The direction of gravity is downwards and the direction of movement is upwards. So here we end up with cos 180, which is minus mgh. Right. Change in potential energy. Right. That is always EP final minus EP initial. And that will be final EP there, mgh, minus initial potential energy. It was at a height of 0, so it had no potential energy to start with. So I end up with mgh. Right, now, the work done by gravity is therefore negative the change in potential energy. Right, and you can go and check that with any situation that you want to, and you will always find that to be true, and you may use that in the exam, right? But what specifically do we want to do that? We want to say if I've got W net, which is equal to the change in the kinetic energy, then that net work is the work done by my conservative force, gravity, and the work done by all the rest, the non-conservative ones. And now, the only conservative force working is gravity. Right, and what do we know about gravity? Gravity is just equal to minus the change in potential energy. And if I rewrite that up, I end up work done by the non-conservative force is the change in kinetic plus the change in potential energy. And once again, you will recognize this, and it is on your information sheet. You can use that, right? The work done by the non-conservative forces are equal to the change in kinetic and the change in potential energy. Right, but we're still not finished with using our non-conservative forces. Now let's think about something where you've only got gravity, right? Where gravity is the only force working on it. Say, for instance, you have an object that is in free fall. Free fall, gravity is the only force acting on that object, and gravity is a conservative force, right? So if we work with W in C equal change in EK plus change in EP, if I'm working with something where there's only gravity, which is conservative, there's no non-conservative forces. So then we'll have a 0 there. If you've got only gravity that is conservative, you have no non-conservative forces to do work. Right, so that's a 0. And then we get to delta. And now, what is EK plus EP? EK plus EP is actually mechanical energy, right? So that tells me the moment that you don't have non-conservative forces, when you've only got conservative forces, then the change in mechanical energy will be 0. And if there is no change, right? It's not the mechanical energy that is 0. There's no change in mechanical energy. And if it's not changing, then it tells me that E mechanical stays the same. Right? It actually stays the same. And stays the same, that means it is conserved. That is what conserved means. It stays the same. So if there's no non-conservative forces, if I've only got my gravity, my conservative force, then it tells me that mechanical energy is conserved. So my conservative force is conserving my mechanical energy. And if it doesn't change, if it stays the same, it means my mechanical energy before is equal to the mechanical energy after the movement, right? And there we have conservation of mechanical energy. Now remember, conservation laws you won't find on the information sheet, right? But you may use them. You have them in words in the exam guidelines. It's just not in this equation state on your information sheet, but you are allowed to use that. Now we've talked about conservative forces, and I would like to do one example. So let's look at the November 2019 question 5. Right. They told you an object of mass 1.8 kilograms slides down a rough. Now that word rough is definitely indicating something. It's indicating that we've got friction down here, right? And passes a point A at which is 1.5 meters above the ground at a speed 0.95. It reaches the point B with 4, which is very nice. They wrote everything onto my diagram, so everything is over there, right? Moving on to the first question there. Define the term conservative. We've already looked at that. Name the conservative force acting on the object, and that will be gravitational force, right? The other two examples were elastic and electrostatic, and they are not in this situation. Right, then they're asking, is mechanical energy conserved? Now, when is mechanical energy conserved? Mechanical energy is conserved, it stays the same when you have only conservative forces, when gravity is only working on this. And this is not true, right? We've got a frictional force. So the answer was no. And then you had to say there's friction, or to say there's a non-conservative force, or even to say it's not a closed system. Right, next, calculate the gravitational potential energy of the object. Now, guys, don't go thinking difficult. Always start and try the easy way. The easy way would be to say potential energy is given by mgh. And they give us the mass of that object. It's 1,8. We have the g, which is 9,8. And remember, this is energy. So don't go putting plus and minus over there. In an energy equation, you just use the magnitude, right? And then the height, 1.5. So this was very easy. And it was 26,46 joule, right? 26,46 joule. Right, moving on. Use energy principles. What does that tell you? No equations of motion, right? To calculate the work done by friction on the object as it slides down. Now, let's quickly think about all the forces acting on this object. So you've got your frictional force working backward. You've got your normal force, and what do you know about normal force? That's always perpendicular to the surface and therefore perpendicular to the movement. So the work done by that normal force will always be 0 joule, right? It's always perpendicular. It's always got a 90-degree angle. Right, and then we look at gravity. Now here we actually got a problem, because at the moment that is the angle with the direction of movement, but soon it will be down here. And then that will be the angle. Can you see that angle is changing? Right. So I've got a problem. If I want to work it out, I don't have an angle to put in there. Right. But if I don't have an angle, then I can work with only that friction, which is my non-conservative force. So I'm working with my non-conservative force is equal to change in kinetic plus change in potential energy. Right. So the normal force is not doing work. Gravity is a conservative force, so this is not part of the non-conservative. The only non-conservative one is friction. Right, and that will be half mv final squared minus v initial squared. Right, this one you can substitute, or you can just say it is EP final minus EP initial. Right. Okay, so here we have half 1,8, 4 squared, right? Because that's the velocity at the end, minus 0,95 squared plus. Now, final EP down here, no height, so we will end up with this potential energy of 0, and we have already worked out up there, it is 26,46 in the previous question, right? So that is just solving, and you end up with minus 12,87 joule. Did I expect a minus? Yes, because remember, friction is always removing energy, right? So that tells you that energy is removed, and that is what I expected, right? Energy must be removed because it is opposing the movement, right? Now, what is the value of the net work done on the object as it slides from point B and C? And for B and C, they said no friction. So if you look at the forces working over there, it's only going to be gravity down and the normal force up, no friction. And remember, there's not something pushing it forwards, right? It's just the momentum taking it forward. Right, so over there, we've got normal force, gravitational force, they're both perpendicular to the movement. So I can tell you they've got 90-degree angles and they are not doing work on this object. So the net work done on this object will be 0 joule. And that's why the kinetic energy will not change. Remember, the net work is equal to the changing kinetic energy. It will not change. It will continue with 4 meters per second in that direction. Right, guys, that was conservation, conservative forces and non-conservative forces. And I hope you send me a lot more questions, because next week we are still looking at questions on work, energy and power.